Hi, and welcome to video lecture number 4 for the Solutions unit. In this video, we are going to cover dilutions. Okay, so before we get into actually how to calculate out dilutions, we are going to talk about what a dilution is. So increasing the amount of solvent while keeping the amount of solute the same is the definition of diluting something. Okay, so if you look at the image on this slide, the beaker to the left that says stock solution before dilution, you can see that there are 6 solute particles in a very small amount of water, right? We would look at that as compared to the other picture, and we would say that that looks very concentrated. It doesn't look like those solute particles can move very well. They seem to be very close together. That means that it's very concentrated. Now, if we were to increase the amount of solvent while keeping the amount of solute the same, so in this case of the picture, we're adding water, but we still are keeping those 6 solute particles. So we are not adding any solute, but we are adding solvent in the form of water. Now, if you look at that, the picture to the right where it says after dilution, we can say that that is less concentrated because there are less solute particles per volume of water than the beaker to the left. Okay, so when a solution is diluted, meaning that we are adding solvent and that is it, the concentration of that solution is going to be reduced. It's going to go down. Okay, so again, the stock solution on the left, very concentrated. We add water to that, we are going to dilute it. So it's kind of like that coffee example I used in video lecture number 1, where if someone were to put too much sugar into their coffee, they would have to dilute it by adding more solvent, which in that case it was coffee, so adding more coffee to their overly sweet coffee in order to make it less sweet. Okay, so that is diluting something. Now, some examples of dilution. If you ever peer assist for the science department, you might be asked to make a bunch of dilutions because we buy especially our acids, but a lot of our liquid chemicals at very concentrated levels. So for instance, for hydrochloric acid, we actually buy a stock solution that is about a 12.1 molar solution. That is very concentrated for an acid. But if you remember back to all the labs that we've done, you don't use nearly as concentrated of acid because that wouldn't be safe, right? So you use anywhere between a 0.1 molar and a 1.0 molar hydrochloric acid solution. So in order to get that, we have to dilute down our stock solution into those bottles that you use for lab. And to do that, we obviously go through the diluting process, and actually this is more cost effective than it would be to buy the 0.1 molar or 1.0 molar solutions to begin with. Now, there are some calculations we can do to better help us when we are diluting a solution. And this big purple box with the equation is going to be really, really important. And most people have it memorized the first time you hear me say it. It's M1 times V1 equals M2 times V2, or M1V1 equals M2V2. Okay? Both of the M's stand for molarity, and both of the V's stand for volume. The 1's and 2's that you see as subscripts in the equation, those are going to represent the initial or the beginning solution and the final or the desired solution. So the M1 is the molarity of your starting solution or you might hear it referred to as our stock solution. V1 is the volume of the starting solution that we are going to need to make our diluted solution. M2 is the molarity of our desired or final solution. And V2 is the final volume of our desired solution. So how much of that final solution we want out at the end. Okay. Now, molarity has a very specific unit, and it has to be moles per liter for molarity. But the volume, V1 and V2, they can change as long as they are in the same unit. So if V1 is in liters, V2 has to be in liters. But if V1 is in milliliters, V2 must be in milliliters. Okay, it's fine if you use different units for volume as long as V1 and V2 are in the same unit. And if you were to choose to use milliliters for the volumes, you do not need to do anything to the molarities. It just works itself out. Okay, so if you change one of the volumes to milliliters, make sure the other one is in milliliters. And again, you don't have to do anything to the molarities. Let's try a practice problem. The question reads, how many milliliters of a 3.5 molar sodium hydroxide solution are required to make 350 milliliters of a 0.25 molar sodium hydroxide solution? Now, the easiest thing that I have discovered when doing these problems is to write out each of your variables and determine where these fit amongst those variables. And then we can put the equation together. So I'm just going to write out M1, V1, M2, V2. One of these is my unknown. The other three were given in the problem. So let's start at the beginning. It's asking how many milliliters of a 3.5 molar sodium hydroxide solution are required to make another solution. Meaning these values, the milliliters I'm supposed to calculate, and the 3.5 molar, those are for my initial solution. So I'm being asked to find V1 in milliliters, and this 3.5 molar is my M1. Okay, whatever I'm using to make something else or to make that second solution is my M1 and V1. So these must be my M2 and V2. We want to make 350 milliliters of a 0.25 molar solution. So my M2 is 0.25 molar. My V2 is 350 milliliters. Now I need to check and make sure that my volume units are going to be the same, right? So if I have V2 as milliliters, my V1 will come out as milliliters. And now I can set up my equation. So M1 times V1 comes first. I'm going to put the 3.5 molar as M1. The V1 is what I'm trying to find, so I'm going to put that in as X is equal to M2 times V2. My M2 is 0.25 molar. My V2 is 350 milliliters. Now I can plug and chug. So I'm going to start by doing 0.25 times 350, and you get an answer of 87.5. So that is equal to my 3.5 molar times X. To get the X all by itself, right, this is algebra, basic algebra, we are going to divide each side by 3.5 to get our X alone. So I'm going to plug in 87.5 divided by 3.5 to get an answer for X of 25 milliliters. So that's saying that I need 25 milliliters of my beginning solution, which is 3.5 molar, in order to make 350 milliliters of the 0.25 molar second solution. So I would put the 25 mils of my beginning solution into a flask or a beaker, and I would add enough water to get that volume up to 350 milliliters, and the ending molarity would be my 0.25. Let's try another problem. What is the molarity of a solution of potassium chloride if 50 milliliters of a 1.25 molar potassium chloride solution is diluted to a total volume of 400 milliliters? Again, the easiest way that I've found to do these problems is to write out each of the 4 variables and plug your known values into those variables to understand how you're going to set up the equation. So I'm going to start by writing out M1, V1, M2, and V2. So I'm going to look at my problem here. It's asking what the molarity of a solution of potassium chloride is if 50 milliliters of a 1.25 molar solution is diluted to another solution. So this 50 milliliters of a 1.25 molar is diluted to make a second solution, which means that the 50 milliliters and the 1.25 molar are going to be my stock solution or my initial solution. So this 1.25 M will be my M1, and the 50 mils will be my V1. That's what I'm starting with. We're diluting that to a total volume of 400 milliliters. That means that this must be my V2. And I'm asked to find the molarity of that solution, so I'm asked to find M2. And that's going to be molar as my unit. Okay? Now I want to check and make sure my volume units are the same. They are both in milliliter, which is great, so I'm going to keep them that way. We don't need to convert anything. Now I can plug them into this equation. So M1, which is 1.25, times V1, which is 50, is equal to M2, which is going to go in as X because that's my unknown, times my V2, which is 400 milliliters. Okay, first thing I'm going to do is multiply 1.25 by 50. You should get an answer of 62.5. So that is equal to my X times 400. Now basic algebra, right? We divide both sides by 400 in order to get X by itself. So 62 divided by 100, or 400, you should get X to equal we'll round it to 1.6 molar. So that's your answer. Your second solution is going to be a 0.16 molar solution. If you take 50 milliliters of your stock or your initial solution, put that into a beaker or a flask, and then fill it up with water until the total volume inside of that beaker or flask is 400 milliliters total. And then what you have in that beaker or flask will have this molarity.